Have you ever looked up at the night sky? Have you ever wondered what's really out there? What if everything we've ever detected with our telescopes is just a tiny fraction of what truly exists? It challenges our place in the universe. This isn't just a philosophical puzzle, it is one of the biggest questions in science today. The stars and galaxies are our lighthouses, hinting at something vast and unseen that holds it all together. Our science has only revealed the tip of the cosmic iceberg, so I invite you to join me on a journey into the shadows of the cosmos. Today we're diving into one of science's most perplexing mysteries, dark matter. It emits and reflects no light, making it utterly invisible. It passes through us and the entire planet. Yet astronomers believe it makes up 85% of the universe's matter. When observing distant galaxies, something didn't make sense. Stars on the outer edges were moving too fast. This suggested extra gravity, implying more mass than we could see. Hence the name, dark matter. Is it a new particle or a flaw in our understanding of gravity? What if dark matter doesn't exist and it's just a placeholder for our ignorance? This brings us to the heart of a raging debate in the scientific community. It's a debate that pits observation against theory, and known physics against radical new ideas. On one side, we have the proponents of dark matter. They argue that the evidence is overwhelming. It's not just the spinning of galaxies. The way light from distant objects is bent as it travels through space, a phenomenon called gravitational lensing, also suggests the presence of massive invisible structures. Computer simulations of the universe's evolution only work if you include this mysterious, unseen substance. Without it, the universe we see today simply could not have formed. For these scientists, dark matter is a tangible physical thing. It is likely composed of exotic particles that we just haven't been able to detect yet. They are building massive, incredibly sensitive experiments deep underground, shielded from cosmic rays, hoping to catch a fleeting glimpse of a dark matter particle as it bumps into an atom of normal matter. They believe we are on the cusp of a monumental discovery, one that will add a whole new family of particles to our cosmic zoo. For them, dark matter isn't a ghost, it's just very, very shy. We are not inventing a concept, we are uncovering a new layer of reality. But on the other side of this great cosmic debate, there are the skeptics. These physicists and astronomers look at the same evidence and draw a radically different conclusion. They ask a bold question: what if the problem isn't missing matter, but our understanding of gravity itself? Perhaps Newton's and Einstein's laws, which work so perfectly in our solar system, begin to break down over the immense scales of galaxies and galaxy clusters. Maybe gravity behaves differently in these vast, empty realms. This idea is the foundation of alternative theories like MOND or modified Newtonian dynamics. These theories propose that there is no dark matter at all. Instead, they suggest we need to rewrite the laws of physics. It's an audacious and unsettling idea. Our theories of gravity are pillars of modern science, tested and confirmed countless times. To suggest they are incomplete feels almost like heresy, and yet the dark matter particle remains elusive. Decades of searching have turned up nothing. This leads to the central question of our journey. Are we discovering something new, or are we simply inventing a concept to explain our own ignorance? Is dark matter real, or a collective scientific illusion? What is dark matter? It's not empty space or dark clouds, it's a substance fundamentally different from anything we know, the invisible majority of the cosmos. Dark matter makes up 85% of all matter. It doesn't interact with light, light passes right through it. It interacts through gravity, tugging on things we can see. We can't directly observe it with current technology. Dark matter is science's ultimate black box. So, if we can't see it, how did we first suspect it was there? The story begins with a kind of cosmic crime scene. The victims? Well, stars on the edges of galaxies. The culprit? An impossibly high speed. In the 1970s, an astronomer named Vera Rubin was studying the Andromeda galaxy, measuring how fast its stars were orbiting the galactic center. She expected to find that stars farther out would move more slowly, just like the outer planets in our solar system orbit the sun more slowly than the inner ones. This is a basic consequence of gravity. The farther you are from the central mass, the weaker its gravitational pull. But that's not what she found. To her astonishment, the stars on the very edge of the galaxy were moving just as fast as the stars closer to the center. In fact, they were all moving at incredible speeds, far too fast for the galaxy's visible mass to hold them in their orbits. According to Newton's laws of gravity, these speeding stars should have been flung off into deep space like a child letting go of a spinning carousel. The galaxy should have been flying apart before her very eyes, but it wasn't. it was stable. It was holding itself together. This observation created a massive puzzle. There was clearly not enough gravitational glue from the visible stars and gas to keep the galaxy intact. It was as if an invisible hand was providing the extra gravity needed to hold on to those fast-moving outer stars. This discrepancy between the observed motion and the expected motion was the first smoking gun. Something else had to be there, something massive, yet completely invisible. This something was the missing mass, what we now call dark matter. It was the only explanation that made sense without throwing out our entire understanding of gravity. Since Vera Rubin's groundbreaking work, we have seen this same effect in countless other galaxies. It's not a fluke, it's a universal phenomenon. Everywhere we look, from small dwarf galaxies to giant spiral ones, we see evidence of this unseen gravitational influence. The stars are all caught in a cosmic speed trap, moving faster than they should, yet held in place by a force we cannot see. The conclusion became almost inescapable. Galaxies must be embedded in vast spherical halos of dark matter like a marble inside a much larger invisible bowling ball. The evidence for dark matter doesn't stop with spinning galaxies. Scientists, like good detectives, look for corroborating evidence from multiple, independent lines of investigation. One of the most powerful pieces of evidence comes from a phenomenon predicted by Albert Einstein himself: gravitational lensing. Einstein's theory of general relativity tells us that massive objects warp the fabric of spacetime around them. This curvature of spacetime dictates how other objects, and even light, move. So a massive object can act like a lens, bending the path of light that passes by it. Imagine looking at a distant candle flame through the base of a wine glass. The glass distorts the image of the flame, making it appear warped or even creating multiple images. In the same way, massive clusters of galaxies can act as giant cosmic lenses. When we look at galaxies that are even farther away, behind these clusters, their light gets bent and distorted as it travels to us. The resulting images are often stretched into strange arcs, or even appear as multiple images of the same galaxy. This effect is called strong gravitational lensing, and it's a spectacular confirmation of Einstein's theory. Here's the crucial part. When astronomers measure the mass of a galaxy cluster based on all the visible matter, the stars, gas, and dust, it's not nearly enough to produce the amount of lensing we observe. The light is being bent far more than it should be. The lens is much stronger than it appears. To account for the observed distortions, there must be about 5 to 6 times more mass in the cluster than we can see. This extra mass, this gravitational heavyweight, is dark matter. It provides the additional gravity needed to bend the light so dramatically. This is incredibly powerful evidence because it's completely independent of the galaxy rotation problem. One method looks at the motion of stars inside a galaxy, while the other looks at the bending of light around a galaxy cluster. Yet both methods point to the same startling conclusion. The universe is dominated by an unseen substance. It's as if we have a ghost in the cosmic machine. We can't see it or touch it, but we can see its profound effects on everything around it. It's the invisible scaffolding upon which the visible universe is built. The existence of dark matter seems almost certain when you look at the evidence. The speed of stars and galaxies, the gravitational lensing around galaxy clusters, and even the large-scale structure of the universe all point to its presence. Computer simulations that model the evolution of the cosmos from the Big Bang to the present day simply do not work without it. If you run a simulation with only normal matter, you end up with a universe that looks nothing like the one we live in. You don't get the beautiful web of galaxies and clusters we see. You get a clumpy, disorganized mess. Dark matter is the secret ingredient that makes the recipe work. So, why is there a debate at all? Why doesn't everyone just accept that dark matter is real? The problem is simple, yet profound. After decades of searching, we have never, ever directly detected a single particle of it. We have built some of the most sensitive experiments ever conceived. We have gone deep underground into old mine shafts to shield our detectors from any interference. We have used vats of supercooled liquid xenon, hoping that a stray dark matter particle, a so-called WIMP, weakly interacting massive particle, might bump into a xenon nucleus and create a tiny flash of light. And yet, after all this effort, we have found nothing. Silence. The ghost in the machine remains a ghost. This persistent failure to find the culprit has led some scientists to question the entire premise. It has created a deep and fascinating division in the scientific community, a cosmic dilemma that forces us to confront the limits of our knowledge. Is it possible that we are on the wrong track entirely? Could it be that we are searching for a phantom that doesn't exist, simply because we are afraid to question our most fundamental theories? This is where the debate truly ignites. Are we discovering something new, or are we just inventing a concept to explain our own ignorance? One side says, be patient, we just need more sensitive detectors. The particle is out there. The other side says, enough is enough. Maybe the problem isn't a missing particle. Maybe the problem is with our theory of gravity. This is not just an academic argument. The answer will fundamentally reshape our understanding of the universe. It is a choice between adding a new mysterious character to our story or rewriting the entire plot. To understand dark matter's role, we journey to the early universe shortly after the Big Bang. The cosmos was a hot, dense soup of particles with tiny density fluctuations. These seeds of structure were the starting point for everything. Here, dark matter began its crucial work. Normal matter and dark matter competed, both subject to gravity. Normal matter faced radiation pressure, but dark matter, immune to it, could respond solely to gravity. Over millions of years, dark matter formed vast clumps, the first large-scale structures. These became the cosmic seeds for galaxies, creating the gravitational foundation for their formation. Dark matter was the essential catalyst, providing the cradles where galaxies could be born. As the universe expanded and cooled, a critical moment arrived. The cosmos became transparent. Normal matter began to fall into gravitational wells carved out by dark matter, acting like cosmic magnets. This was the beginning of galaxy formation. Dark matter created the large-scale structure. Normal matter settled into the center of dark matter halos. This infalling gas was the raw material for the first stars and galaxies. Dark matter is like an invisible skeleton, dictating the final shape. Without this skeleton, galaxies wouldn't exist or hold themselves together. Dark matter ensures the stability of every galaxy, including our Milky Way. The story of galaxy formation is a tale of two kinds of matter. Dark matter clumps together to form massive halos, creating the universe's gravitational landscape. Normal matter is messy. Its particles collide and radiate energy as light. As normal gas falls into a dark matter halo, it cools and collapses, forming a dense rotating disk. This explains the structure of a spiral galaxy, a dark matter halo with a bright disk of stars, gas, and dust. This cosmic partnership between dark and normal matter drives galactic evolution. The visible universe is just the luminous tip of a much larger, darker iceberg. Dark matter is the grand architect of the entire cosmic structure. Using telescopes, we see galaxies arranged in a breathtakingly beautiful pattern we call the cosmic web. Galaxies cluster into filaments and massive nodes, separated by cosmic voids. Its existence is powerful evidence for dark matter. Simulations show dark matter halos forming along filaments. Without dark matter, this cosmic web wouldn't exist. Dark matter is the silent weaver that has spun the very fabric of the cosmos. Mainstream cosmology says galaxies can't form without it. It explains the speed of stars, the bending of light, the formation of galaxies, and the universe's large-scale structure. Despite compelling evidence, the case for dark matter faces a glaring problem. It's the elephant in the laboratory. After decades of searching with sophisticated experiments, we have failed to find a single particle. This failure strikes at the heart of the dark matter hypothesis. We've built detectors deep underground, shielded from cosmic rays. Experiments like Lux Zeppelin use liquid xenon or argon, hoping a dark matter particle bumps into an atomic nuclei. Yet every experiment has come up empty. What if we're looking for something that simply isn't there? Maybe the problem isn't with our detectors, but with our theory. Maybe there is no missing matter. What if our understanding of gravity is incomplete? Einstein's general relativity has passed every test in our solar system, but it may not tell the whole story. We've only tested gravity in strong fields, like here on Earth or near the Sun. But the outer edges of galaxies where the dark matter problem appears are regions of ultra-weak gravity. Could gravity behave differently in these environments? Maybe it doesn't fade as quickly as Newton and Einstein predicted. History shows us that scientific laws can be expanded. Newton's laws worked until Einstein revealed their limits. Now, some scientists argue we're at a similar turning point. Perhaps general relativity is just an approximation, and we need a new theory for the cosmos. This is the core idea behind alternative theories that challenge dark matter. Maybe we don't need new matter, just new physics. Instead of adding invisible ingredients, perhaps it's time to rewrite the recipe itself. The persistent absence of a dark matter particle forces us to consider this bold path. The leading alternative is MOND, modified Newtonian dynamics proposed by Mordechai Milgram in the 1980s. MOND tweaks Newton's law below a certain tiny acceleration. Gravity gets stronger than expected. This simple change explains why stars at the edges of galaxies move faster, no dark matter needed. MOND elegantly predicts the relationship between a galaxy's visible mass and its rotation speed, something the standard model must fine-tune. But MOND isn't perfect. It struggles with galaxy clusters and isn't fully compatible with Einstein's relativity or cosmology. While it solves some problems, it creates others. Still, MOND's successes force us to question whether we need dark matter or just a new law of gravity. The debate remains open. Is dark matter just a modern god of the gaps, a placeholder for what we can't explain? Critics argue we invoke dark matter whenever gravity doesn't match observations, adjusting its properties to fit the data. This flexibility risks turning dark matter into a cosmic fudge factor, masking deeper problems in our theories. Yet defenders point out that dark matter is a testable hypothesis, not a supernatural fix. It predicts features like the cosmic microwave background that alternatives struggle to explain. The search for dark matter is science in action, messy, uncertain, and driven by evidence. If we never find dark matter particles, when do we admit it's time to rewrite physics? There's no easy answer, only the relentless pursuit of truth. Dark matter is thought to be the architect of the universe's largest structure, the cosmic web. Galaxies aren't scattered randomly. They form vast filaments and clusters, separated by immense voids. This intricate pattern matches predictions from dark matter models. In the early universe, dark matter collapsed into a web-like skeleton, drawing normal matter into its filaments. The densest nodes became galaxy clusters, filaments became cosmic highways, voids the empty countryside. Computer simulations show this web forms only with dark matter's gravity. The cosmic web explains why the universe is structured, not chaotic. We live in a neighborhood shaped by an invisible force we can't see, but whose influence is everywhere. Let's run a cosmic thought experiment. Simulate the universe with and without dark matter. With dark matter we get a rich cosmic web, filaments, clusters and galaxies just like we observe. Remove dark matter, and the universe forms slowly, with few small clumps. No grand structure. Without dark matter, gas can't collapse efficiently, delaying or preventing star and galaxy formation. The universe would be a dim, empty place. Nothing like our own. This stark contrast is a powerful argument for dark matter's existence. Our very existence may depend on this invisible ingredient. Without it, the universe and life might never have emerged. Dark matter's influence shapes not just the cosmic web, but the fate of galaxies within it. Galaxies feed on gas funneled along dark matter filaments, fueling star formation for billions of years. A galaxy's environment, void, filament, or cluster, determines its growth and destiny. In clusters, galaxies collide and merge, often losing their gas and ceasing star formation. This explains why some galaxies are vibrant spirals, while others are old, red, and dead. The dark matter framework guides the entire life cycle of galaxies. The universe's diversity of galactic forms is a direct reflection of this invisible landscape. We're witnessing worlds built on a framework we can only infer. The dark matter model produces a universe that looks just like ours, explaining the cosmic web and the diversity of galaxies. But this success leads to a critical question. Are we seeing the truth, or a reflection of our assumptions? This is where we confront confirmation bias, favoring information confirming our beliefs, and ignoring contradictions. Are we discovering dark matter's role, or have we built a model designed to do exactly that? The cosmic microwave background provides an independent check, aligning well with the dark matter hypothesis. Skeptics and alternative theories force us to re-examine assumptions. Questioning and challenging keeps science honest, ensuring we push toward a deeper truth. Science is a fundamentally human endeavor, not a straight line to the truth. It's filled with brilliant ideas, dead ends, and fierce debates. The story of dark matter exemplifies this. But what happens when a theory leaves nagging questions unanswered? It begins with doubt, and the courage to question our most cherished beliefs. The history of science is filled with examples of brave thinkers who dared to suggest that the consensus was wrong. Alternative theories are essential for the health of science itself. What if cosmic discrepancies aren't due to invisible matter but a new law of nature? Exploring alternatives is a sign of a robust field. Science progresses through doubt, not certainty. Let's look at MOND. Its core idea is simple. Gravity behaves differently where its pull is extremely weak. This allows MOND to explain the rotation speeds of galaxies with precision, often better than dark matter models, without new particles. This is MOND's strength. its simplicity and predictive power on galactic scales. However, MOND struggles with larger structures like galaxy clusters. Even MOND needs to invoke some missing mass. More sophisticated versions, like TVS, try to address a wider range of cosmic phenomena, but they haven't replicated the success of dark matter in explaining the cosmic microwave background. Dark matter provides a consistent explanation across all cosmic scales. MOND remains a persistent challenger. MOND has seen successes, but the scientific community largely favors the dark matter hypothesis. Why? The standard dark matter model, lambda CDM, has woven together many observations into a coherent story. Thousands of careers and entire fields of experimental physics are dedicated to it. To propose abandoning it is a revolutionary act, reflecting the immense investment in the current model. MOND hasn't provided that undeniable smoking gun. Modifying gravity questions Newton and Einstein's legacy. Science progresses through tension between conservatism and revolution. It sets a high bar for challengers. The debate continues, demanding rigorous evidence for new ideas. We stand at a fork in the road, faced with two paths to understanding our universe. One path follows the standard model of cosmology, a universe filled with dark matter. This path explains the speed of stars and galaxies and the structure of the cosmos. Believers hope our detectors will reveal the dark matter particle. On this path, dark matter is real, an elusive, undiscovered frontier. Finding it requires patience and better tools to unearth this cosmic secret. This path suggests a parallel world of particles interacting through gravity. It's a path of discovery, adding a new character to our cosmic story. Now let's consider the path less traveled. To walk this path is to question the very foundations of our knowledge. It is to entertain the idea that dark matter is not a substance but a symptom of a deeper misunderstanding of gravity. This perspective argues that the continued failure to detect a dark matter particle is a sign that we are looking for the wrong thing. Theories like MOND show that by making a small change to how gravity works, we can explain the motions of galaxies without dark matter. It follows Occam's razor. The simplest explanation is often the best one. So, where do you stand? Which side of this cosmic debate do you lean toward? There is no right or wrong answer right now. Your perspective is a part of this ongoing human story to understand our place in the cosmos. We have traveled to the heart of a cosmic enigma, a debate that divides the greatest minds in science. We stand at a precipice of knowledge, staring into a profound darkness. The answer to this grand question will not be found in what we choose to believe. It's about the process itself. It is about the relentless human drive to ask questions, to challenge answers, and to never be satisfied with "we don't know," and to remain humble in the face of the vast, silent cosmos. We are pattern seekers. We are storytellers. The theory of dark matter is our current epic tale. It's about a method of questioning, for systematically stripping away our own biases and misconceptions until we are left with a clearer view of reality. It is the questions themselves that have the power to reshape our universe. As our journey comes to a close, we are left not with a final answer but with an open-ended challenge. The cosmos has laid a puzzle at our feet, and its solution will undoubtedly mark a new chapter in the history of human thought. It would confirm our cosmological model and set the stage for the next generation of questions. But what if we find nothing? That outcome, in many ways, would be even more exciting. We are poised between two incredible futures. Either outcome represents a giant leap in our understanding. Only a universe waiting to reveal more of its secrets. Keep looking up, keep asking questions, and that is how we, together, continue our journey into the cosmos.